Okay, so this is day 2. We'll be talking about definite integrals as area. Okay, so these are the 5 rules that we're going to be talking about today. Okay, the first rule of definite integrals is if your upper and lower limit are the same in a definite integral, there's no area. It's automatically 0. Rule number 2 says if you switch your upper and lower limits, then you change the sign of your integral because it changes the direction that you're taking it. Okay. The third rule says that if you have this part the same, you can split your integral into 2. Okay. 2 different integrals. One starting from A to C and the other one starting from C to B. That C value does not matter. You can pick anything you want in between A and B, and you can split it up into 2. Okay, there's the constant multiple rule. So just like in derivatives, when we took the derivative, we could pull the constant out. Here in an integral, we can actually take the constant out of the integration altogether. Okay, and then the last rule basically says that if I have 2 functions inside an integral being added or subtracted, I can split it into 2 as long as I keep my definite integral limits the same. Okay, and that's basically, like I said, the same thing for derivatives. It's the sum rule of derivatives. It says if I have 2 functions that are being added together, I can take the derivative of each one separately. Okay, so this first one. So we've got this graph. That's our f. Okay, it says evaluate the following definite integrals. So number 1, it says I'm taking the integration from 2 to 6 of f of x plus 6 dx. Okay, and in this one, we're going to be using rule number 5. I'm actually going to split this into 2 integrals. So I'm going to change it so that I have the exact same limits for both. Now the area from 2 to 6 of my f of x, that's the area from here to here. So this is just a triangle, so we use our geometric. So the height is 4, the base is 4, so 1/2 base times height, so this is going to be 8. Okay, now, so this is 8 plus the integral for this. Remember what we're doing here. Basically, this is the height times the width, or the change in x. My change in x is from 2 to 6. So basically this is 6 times 4. Because my height is constant. If we graph that, that's a constant function. So basically this is the area under of a rectangle. So this is basically just 8 plus 24, which is 32. Okay? It wouldn't have been any different if I had just taken this area right here. If I had just taken this area right here and shifted it up 6, because that's what this is telling me to do. If I just took that triangular area and just shifted it up 6, I would have made a rectangle underneath it that was basically 6 units high and 4 units wide underneath that part of the function. And that's what this represents, this integral right there. It basically represents that shift up 6. So our transformations hold true with our areas. Okay. Let's look at the second one. I've got the integral from 0 to 6 of 2 f of x dx plus the integral from 6 to 10 of 2 f of x dx. So since this part right here and this part are the same, I can actually put these together and just find the integral from 0 to 10 of 2 f of x dx. Also, I can take this 2 to the outside of my integration. So I just have to deal with this. Okay? Because again, this 2 is basically a vertical stretch. So if I vertically stretched it, I'm basically multiplying my y values by 2, and that's the area by 2. Or I can find the area first and then just multiply that area by 2. It doesn't make a difference. So now I have to find the area from 0 to 10. Well, we know this part is 8. So from here to here, base is 2, height is 4. So 2 times 4 is 8 divided by 2. This is 4. This area right here from 6 to 10. This is negative 8. And then this area right here is negative 4. So basically the area from 0, we're only going from 0 to 10. So that is going to be 4. So this is 2 times 4, which is 8. That's it. Okay. All right, now the last one. So we've got this integral from negative 4 to 0 minus the integral from 12 to 0. Well, the first thing I notice is that this integral right here, the bigger numbers on the bottom, and that's not really the way we do things. So the first thing I'm going to do is rewrite this. 0 dx. I'm going to switch my limits, okay, so that the smaller number's on the bottom. So it'll be from 0 to 12. But in doing so, that changes the sign on my integration. So we get minus and negative, which makes this plus. So now I'm taking the integral from negative 4 to 0 and adding the integral from 0 to 12, which, just like the last one, this means that this is basically the integral from negative 4 all the way to 12. So it's the area under everything, all the way from negative 4 to 12. Well, we already found these parts here. This part here from negative 2 to 0, that's going to be 4. And then this part here from negative 4 to negative 2 is negative 4. So when you add all of these up, you've got negative 4, negative 8, negative 16, positive 16. So the answer is 0. Okay. Remember, we're talking about net change. Okay. So we're adding up positives and the negatives, finding how far it is from its original starting point. So if you think about this is velocity curve. So think about f of being v of t. That means that the area underneath this curve is the distance that's traveled, or when we use the integral, it's telling us displacement. So from here to here, it's gone negative 4, backwards 4, forwards 4, forwards 4, forward 8, backwards 8, backwards negative 4. So basically, we ended up where we started. Okay. So when you think about it as velocity, sometimes the integral makes more sense when we do area under the curve. But these rules for definite integration definitely are going to come into play big time. Actually, this graph is off of one of the old AP exams. So you'll see things like this on the AP test.